Hi. A while back I mentioned I'd installed some PV panels and battery storage to supplement the power here at home, and that's been working really well all over summer. In fact, we haven't used any energy from the grid really since about May, but we're just getting to the time of year now where we're starting to get a few more cloudy days, and occasionally we have to draw some power from the grid, or we have to try and charge the batteries. Now, there's lots of ways that you can do that, lots of energy tariffs available which allow for cheaper charging of the battery overnight, that kind of thing. I'm currently with Octopus, which is one of the energy suppliers in the UK, and the tariff that I'm on is Intelligent Octopus. And when you have one of these Ohme chargers, this is the Ohme Home Pro, but they do a few others, you get cheap rate electricity between 11:30 and 5:30 in the morning. So at the moment it's about 7.5 pence per kilowatt hour instead of closer to 30 pence. So there is a reasonable saving to be had by charging the batteries overnight if we know it's going to be cloudy the next day. The problem is when you use one of these chargers on Intelligent Octopus, as well as those 6 hours, they will sometimes allocate you extra hours during the day. And the problem with customers that have battery storage is there's no way, as it stands, for you to get any information from one of these EVSEs or from Octopus when those hours are being allocated. And what happens is if you happen to plug in an EV and they allocate you hours during the day, it'll just draw power from your batteries. There's no way to tell the inverter that we're on cheap rate and to draw power from the grid instead. So we're going to have a look inside this unit, and we're also going to explore how it works a little bit, but ultimately what I want to do is develop a little board that hopefully we can put inside here that will signal to something like Home Assistant that it's currently charging, it's been allocated some cheap rate hours by Octopus, and to change the settings of the inverter. In my case it's a Solis inverter, which is already quite poor in terms of integration, so we've got to do some work on that as well. But I'd like to be able to signal from this unit that it's charging and to draw power from the grid and not from the batteries, because I don't ever want to draw power from batteries to charge an electric vehicle. So to facilitate the exploration of how this EVSE works, I've had this little board made which is intended to simulate an electric vehicle being connected to the EVSE, and this was manufactured at our sponsor for this video, PCBWay, and this is actually a very small board, so this is one of the first times that I've actually used the cheapest option at PCBWay. I had 5 of these boards made. It's less than 100 by 100 millimeters. I just had it made with green 2-layer PCB, and that means it comes in at just $5 for the PCB. And what's really nice is it's super quick to get a simple 2-layer board manufactured. This was made in 24 hours, and because I used DHL for shipping, it actually arrived in only 3 days, which I think is really impressive from our sponsor. So what this is a series of switches that switch in various resistors and that kind of stuff to simulate how an electric vehicle communicates with one of these EVSEs in the simplest mode. There are various vehicles that have other APIs that allow it to communicate in a more intelligent manner, but in terms of communications across the cable, there is a standard protocol for this. Now, I found this PCB design on GitHub, and I'll put a link to this repository in the description down below, but it's a series of switches that can select various options for this Type 2 connector on this EVSE. So this is the schematic, very straightforward, and it's this part at the top here which signals to the EVSE that a vehicle is connected and what it should be doing. And you can see there's a table here which shows what would happen with the switches in various positions. But as I said, I'll put a link to this in the description and you can take a look at it at your own leisure. So what we're going to do first of all is just quickly solder up this PCB. There's just a bunch of switches and a few through-hole resistors. It shouldn't take us very long. So we'll use one of the Metcal soldering stations and get this soldered up. So that all went together nice and easily, and you'll notice that there's two banks of switches, and I've connected 3 wires up. One is the earth connection, one is proximity pilot, and one is control pilot. And you'll also notice all of the components on here are passive parts, and it's purposely designed to be a very straightforward system to implement on the electric vehicle. Now there are other things that can work over the top of this. As I said, there's APIs that allow it to communicate wirelessly for advanced functionality, but in its simplest form, all that happens is on the control pilot pin, the EVSE provides 12 volts through a 1K resistor and measures the voltage on the control pilot pin. When an EV is attached, it's connected through a diode and it sees a 2.74K impedance, which drops the voltage here from 12 volts to 9 volts. And all that does is indicate to the EVSE that an electric vehicle is attached. Once that condition is met, then it switches over the 12 volts to a 12 volt 1 kilohertz square wave. And then the EV can tell that the EVSE is preparing to give it charge, and then it can close another resistor, which then indicates that the EV is requesting a charge from the EVSE. And once it sees that voltage drop to 6 volts, then it will turn on the AC connections on the connector. Now, you'll notice there's a diode here. This is designed for protection so that it can tell that these impedances are real and not just from the connector being damp. Obviously, if it was just water on these 2 pins here, then it wouldn't look like a diode. So it's specifically looking for some rectification so that you don't see the negative half of this plus or minus 12 volt square wave. So that's kind of a safety feature. And that is, there's a switch just here which basically shorts out that diode, and what should happen on the Ohme charger is that it should either indicate an error or just stop charging at that point. So we've got a switch here that indicates that an electric vehicle is attached. We've got a switch here that requests a charge from the EVSE. We've got a couple of switches here. So this one provides a very low impedance across here, which technically is a fault condition. And there's another one here, which is the ventilation switch. So if you were charging a lead acid type battery, then this suspends charge so that the air can be exchanged in the vehicle to make sure that there's no explosive gases. Now, this bottom row of switches is associated with the proximity pilot pin, which in this case I don't think is used on this EVSE. It's more for EVSEs that have a socket and where you can provide your own cable, and it indicates to the EVSE and the EV what cable is attached so that it doesn't overload it. So it switches in some impedances that are preset. So I think here we've got 13 amps, 20 amps, 32 and 63 amps, and basically based on the thickness of that cable, these resistors will be preset in that cable so that it knows how much charge can be delivered. And then there's one more switch at the end here which just shorts those that line out. Now in this case I don't think that's used at all, but it's also used as a function to trigger a solenoid in the socket so that you can't pull out the cable mid-charge. Now there's only one other thing here, is this oscillator. It's a square wave nominally with a 50% duty cycle, but certain EVSEs will modulate this square wave, so it will change the duty cycle based on the amount of power available. This is particularly used on EVSEs that have integration with solar PV systems, where you might want to only use the amount of charge that is available from solar and not draw any from the grid. So this is used to vary the duty cycle, and then the EV will vary the amount of power that it draws from the AC connections. Now that's not mandatory. I don't think all vehicles do that, but it's a nice feature that means that you don't draw any power from the grid if you only want to charge from solar. So we're going to look at these waveforms, but we're going to try and hook this up to the Ohme charger and just see what these switches actually do. So we've got the connector hooked up to a socket, and the PCB is connected to the control pilot and proximity pilot pins. We've got an oscilloscope connected to the CP pin so that we can see what's going on. And obviously we've got this powered up. Now, this charger is linked to Octopus, so they can control the charge outside of the off-peak times. The idea is that if there's excess capacity on the grid, then it will allow you to charge a vehicle at 7.5p instead of the peak rate. We're in the middle of the afternoon now, so this may not charge. I may have to override it, but we're not actually drawing any current anyway. So at the moment, no vehicle connected, so we're just seeing the 12 volts on the control pilot pin. If we flick the switch to say that there's an EV connected, then we get the square wave, and it said 50% duty cycle. Now it's dropped down to 10, which is suggesting that we're trying to do some load balancing on the grid, but it turns out Octopus have decided this is an acceptable time to charge, to use some excess capacity, and so actually we're getting cheap rate electricity to the house now. And this is the point that I'm trying to actually fix with this system. There's spare capacity now, and we could, especially on a particularly cloudy day, we could be charging the batteries a little bit rather than just running off the batteries and PV, where we're running the risk potentially that in the evening we might run out of charge in the batteries. So that's why I want to indicate to Home Assistant that we've got some off-peak electricity ready. So it's given us that 10% duty cycle. It did a few things there. I think that's just trying to re-establish communications with the car. But at the moment the car isn't requesting charge. If I flick this switch here, then it is. The voltage drops slightly, and you can see we've now got the AC supply connected. This is a little neon light. So we're now drawing power through this, and the problem is now we would be discharging from the batteries, not from the grid. Now we've got a couple of other switches here. One of them is the ventilation function for lead acid batteries, but this doesn't seem to do anything at all with the ohm charger, so I think this isn't designed for that. We've got a switch here which puts a small resistance in parallel with the others, which technically is a fault condition, but the Ohme charger seems to happily just continue providing power. And then we've got a switch that shorts out that diode for protection purposes, and that does interrupt the power. But what's interesting is there's no warning on here that there is a fault condition occurring. If you were not understanding what was happening, you'd actually think that the car was just charging and nothing was wrong. But I would have thought these indicator bars should go red and say, you know, there's a fault with the cable, which is something it doesn't seem to do. Now these other switches, which were the current carrying capability switches, that doesn't seem to do anything on this particular charger, but I think that's quite normal because it's a tethered charger. So that's all working as expected. Now there must be a CT or something in here because it does have the ability to measure the amount of power being delivered. So I think what we want to do now is just open this up and have a look at what's inside. The unit came apart quite easily, and it separates into two halves. So this is the side that mounts to the wall, and this seems to have all of the power electronics on it. Then there's another PCB for the front panel display. So what we've got on here is the mains cable coming in. There's also a connector off to the front panel, which is for the current transformer, because you can do load balancing with this unit so that you don't overload the AC supply into the house if you're on a limited supply. Then we've got the cable going out to the EV connector, and incidentally there is only the CP pin connected. There's no proximity pilot on this particular unit. We've got a connector here. This header goes off onto the front panel, and on this PCB basically it looks like we've got some electronics here. This is a switch mode converter, so providing power for the electronics on the front panel. So common mode choke, filters, a capacitor, the actual flyback transformer, and all the other electronics must be on the underside. We've also got a couple of Panasonic relays. These are high power double pole relays, very common in these EVSEs. And then we've got a special type of current transformer for the RCD functionality. So this is specifically designed to detect AC and DC imbalance on the line and neutral conductors. Limited range, so this isn't actually designed to measure power being delivered to the EV, which raises the question. I can't actually see where there's any kind of proper current transformer. I think on Mike's video he had an additional transformer on there for measuring current, and this is dedicated for RCD functionality. It can't measure amps differentially of current. So perhaps there's something on the underside of the board, or maybe they're using a shunt resistor. So let's detach all of these conductors and remove the PCB from the chassis. This is the underside of the PCB, and yeah, we've got a current shunt resistor. So this is our incoming connections, line and neutral, and the line connection, without going anywhere, goes straight to the shunt resistor that's marked 0.3 and 1%. Now I assume this is 0.3 milliohms and not 0.3 ohms, because we could be delivering 7.4 kilowatts into an electric vehicle. But you'll notice that there's nothing else before that, and after it is immediately that current transformer for the RCD functionality. So we've got line and neutral, then into the double pole relay, so line and neutral, and this is the outgoing side, line and neutral, and then these are our terminal blocks on the other side, straight to the cable off to the EV. So nothing really in the path there other than the shunt resistor. There is some additional electronics here, we'll look at that in a moment, but the only other thing here is this node here is a fuse, and then that goes to power some of the electronics over here. So everything that is used by the EVSE is monitored by this current shunt. Now there was another relay up here, and this one is the earth connection. So this is our incoming earth, that's our outgoing earth to the EV, and they're using both poles of the relay to switch earth, presumably for redundancy, so they can switch that off as well. So the whole thing becomes completely disconnected from the mains. So yeah, on this side you can see two relays, and that's the special current transformer. Now what we've got here is a switch mode power supply, as I mentioned before, and it's actually this little SOT223 device that's the controller, which confused me for a moment. I thought I couldn't find the controller at all, but here's the datasheet for it. It's an NCP1075, and this is a low power offline switcher, and they've got a couple of taps on here, but basically it's very straightforward design. So yeah, just switches a flyback transformer, and from what I can see on the PCB, there's 3 different taps, and one of them is a tap that comes back through here, through a small linear regulator here, to power this device here. And this is an HT7017, and this appears to be sort of a dedicated smart metering chip. It looks like they're using just 2 of the channels, so there's 2 differential inputs, one for voltage, one for current, and one single-ended current input, and our shunt resistor is connected across these 2 nodes just here through a PGA and then into an ADC, and then all the rest is kind of smart metering stuff. So it communicates with a UART interface, but it looks like it can do all of the usual UART type all of the usual smart metering type capabilities. So you can read the power, the current, the voltage, the power factor, the energy, and all of that kind of stuff the entire time it's powered up, and then there's a pulse output as well. So that's how they're measuring the current into the EV. Now I think the output here is probably only in the low millivolts range, so that's quite a sensitive ADC there. But then on this side there's just a few regulators and a few other bits off to the header that goes off to the front panel. So in terms of getting a signal out to Home Assistant, I think we've got a few options. One of them is to put a little board inside the case for this unit, because there appears to be plenty of room, and then the whole thing is just self-contained and probably the neatest option. So rather than interfacing with any of the mains, I think we would be able to get our power supply from the switch mode converter, and then our signal to say that the vehicle is charging, that we're getting cheap rate electricity, could just come from the input to the relay. So the coil connection will become active when we're supplying power to the EV. I think that's all we need to do, and then that would be very simple. The other thing that we could do is bring those connections out if we're worried about the power supply capabilities of that flyback converter, and then interface with it in some other way, because all of this stuff on this side is isolated from the mains, well actually only up to here. So it's probably safe enough to bring those out of the casework, but I think in terms of keeping everything all self-enclosed, if I use something like an ESP32 or something in there, I don't think we'd be exceeding the power capabilities of this flyback converter, and it could just be a little module that sits in there and beacons out to say the EV is charging. This is the front panel PCB. It's a little bit less interesting than the power one. This is mainly just associated with driving the LCD and running the system. But one thing to note about these chargers is they don't actually have a Wi-Fi connection. These connect to the servers by the 4G network, so there's actually a SIM card just here. This is a mobile modem, so we've got 2 antennas for talking to the mobile network, and there's also a GPS antenna, which I'm not sure why they have on these units. Someone also noticed there was one on my 5G router that I've got up on the roof. I'm not sure why the GPS is needed, whether that is required for connection to a mobile network. I would assume not. But I don't know if they're tracking location of where these are installed or what. Now also there is a infrared LED and detector just here. It looks like for comms, but this doesn't go to anything. There's no receiver on the other PCB, so this must be for some other type of diagnostics, maybe when it's on the production line or something. But it's a bit odd that they put it on this riser board. We've got a super cap over here, some 4-pin connector. Presumably the apps processor is under this metal can, but we can't see what it is. And that's about it really. A couple of DC to DC converters, one for the LCD backlight and one for other power supplies on these modules, but it's all hidden basically in the apps processor that we can't really see. So that's what it looks like on the front panel. So that's a little look inside the Ohme Home Pro EVSE, and I think the next step basically is for me to just design a very, very simple PCB. There doesn't really need to be anything on there at all, other than either an ESP32 or an 8266. We'll get power from this PCB since it's got the switch mode converter, and then we just need to tap off the coil connection to these relays to get our signal to say that the EV is charging, and then we can forward that on to the Solis inverter, hopefully, to tell it to either not charge from the grid but not supply power from the batteries, or to charge from the grid as well. But if you've got any questions about the unit, since we've got it open, don't forget to leave those in the comment section down below. Or if you can think of a better way, as far as I can see at the moment, there's no way with API access to work out when it's able to charge. So let me know your thoughts and comments in the comment section down below. And big thank you to our sponsor for this video, PCBWay. And until next time, thanks for watching.